Our second talk today is Otis Chodosh, who's going to tell us about aged flows and generic regularity.
Great.
Take it.
All right. Yeah, thanks to the organizers. It's sad not to be back at Matrix. The theme of the talk is going to be this conjecture of Huisken, at least so stated in Ilmanen's problem list. Not so long ago, I gave a talk where Huisken was there, and then he kind of denied making such a conjecture. I don't know exactly. I mean, at least he raised some question along these lines. Certainly, he probably wouldn't have said multiplicity one. So this is a bit of a revisionist version of his conjecture, but it's pretty universally attributed to his idea. Okay, and so I'll be a bit vague here, but you can imagine that this means that sort of like all tangent flows are like multiplicity one spheres or cylinders, appropriately scaled. Okay, so I can never remember the scaling. Here, M naught should be let's say closed embedded. And I might talk about higher dimensions, but I'll always talk about hypersurfaces. Okay. And so I should just say two things: that if this was true, we don't know, it's not clear, but if this is true, then, well, for a flow where star is satisfied, so there's only multiplicity one spherical or cylindrical singularities, then first of all, the singular set. So here I mean a flow in the weak sense, so, or you could flow up to the first singular time, either way, depending on your preferences. Singular set is small and well behaved. Okay, and so I'm not going to say what that means because that's not the focus of the talk. Okay, we don't know everything about the singular set, but if you went to Bill's question time, the questions he was asking about the singular set were kind of refined. Like, what if it vanishes if there's a line or a curve in the singular set, what does the curve look like, right? That's like a reasonable question. Whereas for general mean curvature flow, we know nothing about the singular set, right? So, under this condition star, we're at least starting to have a good feeling for the flow. And the second thing is it's a bit funny, but under condition star, mean curvature flow is well posed, right? So there's no non-uniqueness. Okay, so you can't have a singularity and then have two ways of flowing out of the singularity. Okay, and there's also canonical neighborhoods. All right, and this is the resolution of the mean convex neighborhood conjecture. Okay. The first statement would still be true in this vague sense that I've stated it in higher dimensions. The second one is not resolved fully in higher dimensions. There's partial results. Okay. Okay. Okay, so using Huisken's monotonicity formula, the most naive statement you can make about singularities, right, are that they're modeled on self-shrinkers. Okay, so if you know about various types of blowups, this is not the whole story, of course, but the most basic story you can ask is what sort of self-shrinkers can appear. And so for M naught in R3, there's lots of possibilities. Okay. The boring ones are the plane, sphere, the cylinder. Well, maybe some people would say these are exciting, right? But they're the ones that we're hoping for, right? And then, okay, now my pictures are getting worse, but okay. So here, famous example. Well, I guess all these are kind of famous in the mean curvature flow world. So the desingularization of the plane and the sphere. So it's done by Capellas, Klein, and Muller, and Nguyen by using gluing. And recently there was a min-max construction. I guess it's not clear they're exactly the same shrinker, but one would imagine. So there's a min-max construction by these three. There, of course, maybe the one that I should have said before is the unguent torus. Okay, and then So then finally, I'll just say there's this example where you fatten up the platonic solids. So I can't draw this one very well, but if you look in Chops, I think maybe Illman has some pictures of it. Okay, so and I guess there was recently a different by Aosun and Shinjo and someone, I don't remember the last name in that work, but they constructed even more self-shrinkers which are not in this list. Okay. So all I'm trying to say is that in general, one expects that there's there's a lot of self-shrinkers out there. The Huysken's conjecture is that most of these self-shrinkers, right, like these, right, don't arise. So conjecture generically. Okay. Star. Okay, so for me, star will always mean all tangent flows are multiplicity 1 spheres or cylinders. Okay. So an example, right, is if M naught has mean curvature bigger than 0, right? Now there's a there's a huge number of contributions here. But Brian White, Huysken Sinistari. Hasselhoff Kleiner, Huysken, so Brendel, and with Huysken, right? So there's probably more people that should be on this list, but etc. Okay, so in this case, right, then it's known that all singulars are multiplicity 1, and they're all spheres and cylinders. Okay, so well, all right, so I gave an example and I should give a non-example, right? And so the non-example is going to be the following. So choose sigma to be closed non-spherical self-shrinker. Okay, right, choose your favorite one. Actually, I'm not 100% sure that we rigorously know that there is one that's not the unguent torus. Maybe somebody can correct me if I'm wrong, but all right, I'm pretty sure there's more. Numerically, it's strongly believable there's more. And so, well, start at sigma. I'll draw sigma with 2 holes just to be ambitious. And then if you flow, right, well, what is being a self-shrinker means that the flow is just parabolic dilation. Okay, and so the flow has exactly one singular point, right? And the tangent flow at that point is, of course, sigma. Okay, all right. So that's kind of a really trivial non-example, but it's going to be important. I'm going to use it to illustrate some point later. Okay. Are there any questions?
Are there any shrinkers of genus 2?
I don't know. Probably there are. There's no good reason to imagine that there aren't. So the problem is that the only examples of closed shrinkers that we explicitly know, as far as I might be wrong, embedded. So of course there's the unguent torus, and then these sort of flattened platonic solids should be, well, of course have finite, should be compact, but so Chop only did numerics, and in Kedover's proof, it's possible that they have tiny ends somehow. So maybe not tiny. They could have some ends that appear out of nowhere. Although you kind of imagine that doesn't happen. But as far as maybe someone can tell me if I'm wrong, but as far as I know, there's not even any other contenders for compact shrinkers. So I suspect that there's plenty more. We're just not clever enough to find them yet. The fun thing about making conjectures of this kind, which Huysken may or may not have done, but one of the great things about making a conjecture of this form is that you definitely don't ever want to say what generic is until you've proven some theorem, right? Because generic should be most of the time, but there's lots of different notions in analysis of generic. And so for today, you should think of it as like open plus dense. You know, some sort of bare category theoretic notion. Okay. So I'm going to be a little sloppy about this. So let me show you the following. So openness is kind of for free in these dimensions. I mean, not for free, but openness is true in these dimensions. Like it's not for free. That's not the right way to put it. Let me just show you what that how you could prove that. So because that's kind of a nice application of some recent work in mean curvature flow. And so what I want to claim is that if M naught has this property, right, and if Mj converges in this sort of as C2 embeddings to M naught, right, then for large J, Mj has this property. This is supposed to be Mj. So this is space-time. So, okay, so suppose, right, my Mj, okay, the Mjs they should be drawn in the same picture, but I can't draw it well enough to do that, right? So suppose that my Mjs are very close to the M naught, maybe M infinity, I don't know, let's say M infinity, right? And the Mjs have some bad singular point. So what that means is that some tangent flow here has multiplicity or it's not a sphere or cylinder. So if I write the flows with the script J, like the brachyflows, I can assume that these will converge to the brachyflow of M infinity. I'm going to be a bit vague here, right? You should really check all the details. But, and so you can, similarly, you can assume that the singular points converge. And so then if you define Huyskin's density, right? So things can become more singular, but they can't, singularities persist under limits, right? So that's this kind of statement. Here, right, this is f of sigma for sigma's like some shrinker associated to tangent flow at x infinity, t infinity. Okay, so by assumption, it's f of the plane, sphere, or cylinder. Okay, right? Because I've assumed that this flow has only multiplicity one sphere, like plane, sphere, or cylindrical singularity, right? So this tells me, right, that this density is less than or equal to f of the cylinder, because that's the biggest possibility, plus little of 1. Okay, right? But now, right, so if you combine Colding, like plus 1, right? This says that under this condition, right, once the little o1 is sufficiently small, then the any like tangent flow for mj at xj tj must have been in this list. Okay, so the point being that in this dimension, you know that the low entropy singularities are precisely the generic ones, right? So they persist under so genericity is an open condition in this dimension. Okay, in higher dimensions, it's actually a little tricky. And I don't, as far as I know, it's not clear that if you have a flow with bubble sheets, so like a S1 cross R2 singularities, it's not clear to me that a nearby flow also is generic in that sense. Okay, so I could be wrong, but I'm pretty sure that's correct. I said I want to say something about generic mean curvature flow, and let's return. Okay, so openness is okay. So we need to do density. So well, all we need to do is that to show that for some initial condition, there's a sequence of initial conditions which are good, which converge back to it, right? That's density. Okay, so that's going to make our life a lot easier because we choose which directions we want to perturb. Okay. So for kind of the rest of the talk, the goal is only going to be to talk about density, not the openness. Okay, so remember, if you take the non-example of the shrinker, you get a non-example of a generic flow, right? And so, well, the most obvious question you can ask is what you should do here, right? So how do you get out of this conundrum? Well, there's two things which are obvious that you should not do, right? So if M naught is a shrinker, you should definitely not set M epsilon to be sigma plus epsilon times some vector, right? That's a bad perturbation of your initial condition because, of course, that's just shifting the flow over. Right? And you should also not, right, that would just shift the flow over in space-time. It's useful to draw these pictures in space-time. Right, but still, of course, there's still a bad singularity. And you should also not do the following. Right, you shouldn't scale the shrinker. And, well, that will also just, let me just think how you do this. Yeah, so then that's like a time translation for the flow. Okay, this is the original one. If you make it smaller, well, that's exactly like moving the vertex of the parabolic cone downwards. Making it bigger would be moving it upwards. Okay. So this is a bad idea. Okay. But what you should do is, according to Colding Minicozzi, you should perturb by the first eigenfunction of the L operator. Okay, so this is the first eigenfunction with the second variation of F, and this is the Gaussian area. Okay, right. And so what you can prove, and so I'm only talking about compact sigma just for simplicity. I'll say some things about non-compact later, but if sigma is compact, when you do this, right, sigma will never Why? Why is that true? So in the paper of Colding Minicozzi, they use an argument based on entropy. Right. So you argue that when you do this, the entropy would go down, and then that prevents future singularities having that big of an entropy. Okay. For today, I want to take the point of view that I guess is Colding. And so in this paper, in some sense, you can think of this as providing an alternative reason for why sigma doesn't arise in the flow. Okay. And so I guess this idea was developed more by Bernstein. Sorry. Okay. So sigma plus. So if you perturb by the first eigenfunction, then what you get is something which is not mean convex. Remember I said mean convex flows have this nice property that all singularities are spherical and cylindrical, but it obeys some inequality that's kind of, if you don't look too hard, it looks a lot like mean convexity. And the amazing thing, this is preserved if you interpret it. Right. If you interpret it appropriately, this condition is preserved under the flow. Okay, and that's a result of Smeltchik. Okay, and so that's the first fact, and the second fact is that the flow with this condition, behaves like h bigger than 0, at least for the singular behavior. Right, so this term is lower order, so it doesn't affect how singularities look. Okay, it of course affects the global picture. Yeah, let me kind of try to draw what happens. So here, this is the t maps to. Okay. And then here, if I perturb inwards, okay, then, well, actually, if I flow up, then I get sort of, I get that this flow forms singularities earlier, probably. Okay. And then, but the singularities are simpler, depending on your point of view, right? Because here you might get a neck pinch, then here you probably have another neck pinch and you flow to spheres, and then you disappear in spherical singularities. Okay, so if you think about this picture, you start to see that when you perturb inwards, according to this first eigenfunction, the Schrinker mean convexity tells you that you have to have only mean convex type singularities, and this is sort of the picture that you should expect. Until now, I've said nothing about ancient solutions, and I guess I'm supposed to say something about ancient solutions, and that is kind of the next game. So let me draw this picture. So this is M0, and here we've perturbed epsilon, and there's some flow, and then naught also has some flow, right? Okay. So if we let epsilon, as epsilon is going back to 0, then m epsilon converges to m naught. So these two flows in space-time become the same. So, but what we could do is we could take this distance and we could dilate parabolically around the origin so that this distance always is 1. Okay. So then here's the parabola. This is t maps to root minus t sigma. Okay. Then we could construct some flow tilde so that the parabolic distance is 1. Okay, so I'm being a bit vague there, but what you should do, so you're letting epsilon go back to 0. Okay, and then you rescale so this parabolic distance is 1, and what you get is the following. So this is the ancient solution. And so what you know is that if you do this rescaling for certain shrinkers, so at least in the compact or asymptotic conicals case, you converge and you get some flow, and so you get MT, an ancient curvature flow. Okay, so that if you rescale appropriately, so this lies on one side of sigma, and I should say, I didn't say this. This function, right? Remember, we're perturbing by the first eigenfunction. Phi is positive because it's a first eigenfunction. Okay, so we push sigma to one side, and then that's why this ancient flow is going to lie on one side of the shrinker, and it's going to converge to sigma as t goes to minus infinity. Right, after rescaling it converges to sigma, and this is even like with multiplicity 1. Okay. That's not obviously true, but that's you can prove that from the construction. Okay, so great. That's nice. But we have this. So we have this sort of ancient solution, and it has these sort of two properties. So I might call this like one-sided. Okay, right, and it converges back multiplicity 1. Okay, and so sorry, and I should also say it's shrinker mean convex. So the singular set is good. Okay. So, okay. Well, I've talked about this sort of out of order, but so we first construct I've constructed this ancient solution, but then one should imagine that ancient solutions model sort of tiny regions in the sort of like a flow from compact initial conditions. Okay, so now let me try to return to the original question. Okay, so let me start with my initial manifold. Then let me embed it in like a local foliation. Not in this local foliation. And so the key is that disjoint MS and MS prime like remain so under mean curvature flow, right? Because we're talking about mean curvature flow of hypersurfaces, so compact hypersurfaces remain, compact disjoint hypersurfaces remain disjoint when you evolve. Okay, so I don't know where my M naught was, but here, suppose that M naught flows into some bad singularity. Okay, so suppose there's a bad singularity for M naught. So then, well, let's suppose I choose a leaf of the foliation MS, which is very close to M naught. Okay, and I flow this. Okay, well, now if I imagine looking at this region, right? So a tiny region around the bad singularity. So of course, if you zoom in around the bad singularity and you just think of the original flow, you're going to get the tangent flow, right? So like parabolically original flow, you get, tangent flow. Okay. Right, that's the usual thing in Huysken Mantoulidis. Tells you that if you do a dilation around a singular point, you get some self-similar solution. Okay. However, if you do the same rescaling, so this is M naught, the nearby flows, okay, you have to adjust the which leaf of the foliation you're considering, because as you rescale, you have to get closer and closer. So you have to be a little careful there. What you should get is an ancient flow. So let me give myself some room. So if you do this, you get an ancient flow. Okay. Okay, so on one hand, because I chose leaves which are disjoint from my central leaf, the limit flow should, as long as I choose it correctly, the limit flow will also lie on one side. Secondly, well, it should converge, this ancient flow should converge to the shrinker sigma, which is the tangent flow of my original scale. And let's, multiplicity 1. That requires some argument, but that's actually not too bad. So you could be worried there is a higher multiplicity, but that doesn't occur here. And so then you ask yourself, right, does M tilde T have nice properties, or at least better properties than sigma? Okay, because if it does, then this is a mechanism by which you've avoided sigma, right? At least locally, you say that like locally the flow of MS doesn't have as bad of a singularity as the central flow did, because this ancient flow maybe had better singularities. So, okay, in general, this problem is not solved, so we don't know the answer to this. But we do know in a few cases some things. So So suppose that we have this setup. So we have an ancient flow lying on one side of our shrinker. Let me assume that the shrinker is either compact or asymptotically conical ends, right? Then, okay, there's some symmetry of this problem, like in parabolically dilate. But up to that symmetry, it's exactly this flow MT that I talked about before. And in particular, it's shrinker mean convex. And it has good singularities. Okay. And so and so the other thing I should say, three, MT loses genus. Okay, so that's very important. So eventually MT becomes genus 0, and this goes back to observation of Bernstein and Wang. If you know their cylinder paper. Okay, and so I think that Christos will talk some more about this theorem. So in particular, right, how do you try to show that the flow is shrinker mean convex? I'm not exactly sure what he'll talk about, so I shouldn't claim that he will, but he at least potentially will. And so you should say here, shrinker mean convexity should be somehow related to the one-sidedness of the ancient flow, right? So that's kind of the trick there. Okay. And so corollary. Okay, so this doesn't construct generic mean curvature flows, but we can prove the following kind of funny theorem. I mean, it's a little bit dissatisfying, but it says that we can do something with this theorem. And so if you have a generic, so something open and dense condition, initial condition, then it flows under mean curvature flow. Maybe it has some singularities. Maybe there's some multiplicity 1 spherical singularities, some cylindrical singularities. That's fine. We don't get too excited if that happens. And then one of the following things happen. Okay, it disappears. Okay, so in other words, like we win. Right. So in this case, right, we had only good singularities until it stops. Okay. Okay, but unfortunately, there's some things that we can't rule out. Okay, So one thing that could happen is the multiplicity of some singularity could be bigger than 1. I don't claim to know that this is not happening generically. You would dream that this never happens. You would, a slightly less ambitious, although very ambitious dream was it doesn't happen generically. We're not making any statement about this. And the final thing that could potentially happen is you see something. And this is kind of related to something Brett talked about. So with a cylindrical end, okay, but it's not a cylinder. And so these are famously conjectured not to exist. I think that this almost certainly doesn't happen generically. Maybe not. Let me not make any explicit claims, but I think we should be able to rule out this as well. But at the moment, that's not ruled out. Okay, so corollary is kind of strange because it says that, well, the good thing happens or 2 other bad things happen. But in particular, what it says doesn't happen is that there's no ungunate torus, right? So there's no sort of asymptotically conical singularity at the first sort of funny singular time. I think I have a couple minutes, so I'll just say one last thing. And so if you look back up here, what we showed is in the case of compact asymptotically conical singularities, an ancient flow on one side has very nice properties. It's unique and equal to something which is shrinker mean convex. But suppose you're a little bit less ambitious, but you want to do something more general. So let me state it this way. Take a smooth shrinker. Singularities would actually be okay, but sigma should not be a minimal cone. And so also assume that sigma is not the round sphere, and sigma doesn't split a line. Okay, so if you know about sort of the dimension reduction, this would mean like parabolically split a line. Okay, so it's the same. So we're assuming that you don't split parabolically or sort of like in time or space. Okay, and you're not the sphere. And so if m tilde t is ancient on one side, sigma n1 over root minus t m tilde t converges to sigma with multiplicity 1 as t goes to minus infinity. Okay. Then for xt not equal to the origin, the density is strictly less than that of sigma. Okay. So, all right, so this takes a bit to unpack, but this says that under essentially very general conditions on sigma, that, well, okay, I don't know that the one-sided flow is shrink or mean convex, so it could have all sorts of strange singularities, right? But in particular, this means that the tangent flow is not sigma. Okay. All right. And so I think I probably don't have time to explain the proof, but actually the proof of this statement, the proof of the first statement is quite long. The proof of this statement is quite short, sort of short. And you can kind of think of this as a geometric Colding Minicozzi. Okay, but here I mean the classification of entropy stable shrinkers. And so let me not exactly say what that means, but if you read the proof, it looks very similar to what they do. They argue sort of that, well, the first eigenfunction versus mean curvature. They say that if it wasn't a sphere, then the mean curvature has to change sign, and you use that. And so that sort of argument comes in almost the same way, but it's sort of twisted around. Okay, and so let me just say that this was then used. You know, the first theorem, I think it's clear why that should be useful. I don't know, maybe you disagree, but I think the first theorem is kind of like a bit clearly useful. The second theorem maybe is totally useless. It's not clear, but actually in some settings it is kind of powerful. And so Felix's student Daniel Holgate sort of used it to improvement of entropy Schulze. Right. So what Daniel Holgate proved is that if you have low entropy, so you know the entropy, if you know what that is, should be less than the entropy of the bubble sheet, say, right? Then when if a non-generic flow could have lots and lots of singularities, you don't know, but a generic flow turns out to have only cylindrical singularities, and then out of this condition, he constructed a flow with surgery and used that to prove the Schulze result. Okay, so I'm running out of time, but I think I'll stop there, but I'm glad to take any questions.
Well, thanks, Otis. Do we have any questions for Otis? Start. I had a really simple question, Otis. For the first theorem you mentioned, maybe you said it, but is that is that only in R2 or?
Sorry. So this works in general. There's a technical, like you should be below this, like for our proof, you should be below the singular dimension. Mm-hmm. So you know, in R7 and lower. But I think that's not a set. I mean, okay, I don't exactly know how to do it, but I'm pretty sure you could remove that. Mm-hmm. But so yeah, this should be true in any dimension, I believe. And it certainly with under a low entropy condition, it's definitely true in any dimension. Mm-hmm. So sufficiently low entropy. But
is there any hint you can give about why, you know, this class of shrinkers
Well, yeah, that's easy to answer in some sense. So this class of shrinkers has the property that if you have an ancient flow with this multiplicity one property on one side, so a priori you converge in sort of C infinity loc. Okay, back, so as you go backwards in time, you look more and more like sigma on compact sets, right? But actually, well, if you're compact, then obviously you get the whole thing, right? But if you're asymptotically conical, so you can see this in my paper with Felix on the uniqueness. So if you're asymptotically conical, actually you're an entire graph for like all the way up to times, to time zero. So okay, your entire graph, you're at a graph at infinity, and at some very negative times, you're actually an entire graph over the conical shrinker. So asymptotically conical singularities are sort of the next easiest thing after the compact. So I think you should be able to do cylindrical ends, but maybe let me not put anyone on the spot. That's not me. And like, I don't want to say, like, I don't want to claim we can do it, but I think it's doable. But if you have a cylindrical end, life is much harder because you're like, the bowl, just the bowl, right, is not an entire graph over the cylinder, even though it limits back to the cylinder. Obviously, the bowl does not lie on one side of the cylinder, so that makes certain aspects of life, you maybe are not worried about exactly the bowl, but there's no soft argument to just immediately get graphicality. Right?
Cool, well, let's thank Otis again then.